And hello, here's Mr. C. This is a recording for the Honors Project 3. It's the first one in the second semester. It's the mechanical toy, so my goal is to give you an overview in this short recording. Mechanically powered means, let me get a pointer here, means we're not using rockets. Even if you love rockets, don't use any explosions. But the harder one is don't use any electric motors or anything like that. And we're not doing any rotational toys, mostly because the analysis of it is rather complicated. For rotational, we would need to calculate moments of inertia, I, right? If this is a weird shape, it's not, I would not be mr squared. So that would be hard. And so keep it to a linear motion, and I'll show you more about that project now. The goals, this is all in the student guide, is that we are solving problems, but we are actually creating a problem, right? We're creating a toy and then analyzing it. We specifically look into its potential energy if you use gravity, kinetic energy. You're going to use potential energy anyhow. You need to store energy somehow. Many of you will use rubber bands. So remember the U equals 1/2 kx squared applies to springs. To get the potential energy of rubber bands, it's sometimes best just to count. So you can say U is proportional to the number of turns you make, to N, where if you have a rubber band and you twist it, you just count how many times you twist it around, and you have some measure of its potential energy. You can compare, for example, potential energy of when n is 10 to n equals 20, or 10 and 12, stuff like that, right? Depending on how many rotations you do. And what I mean with that you'll see in a second, because you're going to design a toy vehicle, and it sounds all more complicated than it is, that runs on mechanical power and moves on land or water or through the air. You're going to design it and test it and explain its design, how you came up with it, how it's used, and the physics concept. Specifically, what is your potential energy you store, what's the kinetic energy that comes out of it. So we're going to analyze their velocity and of course kinetic energy, velocity square, right? You're also going to analyze the acceleration for it, and you're going to do it, and if you have trouble with it, you tell me about how you made it better. The rules are, so it's mechanically powered, I said that already. It must move forward, that's important. So, and that's one of the challenges, because we want to measure its movement, right? Whatever toy you have, you want it to go straight. One of the challenges is if you go on water and you don't have any stabilizers there, it will go like anyway, right? So making it move straight is the challenge in some of these designs. And of course going straight through the air is also tough, but you know, if you come up with something that moves straight, that you can measure between two poles or something like that, that's fine too. So I will not grade on the size of it. It doesn't have to be a big toy or complexity. So don't spend much money. You should find all these materials in your home, or you know, in your refrigerator. I'll show you why I mean that. As similar to the last project, the moon landing, you're going to test it and you document it using photos or a video, and you're going to measure acceleration, velocity, momentum, and the kinetic energy, and you see what you can get out of it. So be creative, right? You can say, hey, I'm going to set this up and one way, and I got that kinetic energy. I set it up a second way, I got that kinetic energy. And is that maybe related, right? And then you tell me, of course, how you designed it, the construction and the performance of your toy vehicle, and how much you would sell it for. No, that I'm just kidding. So here's an example, the one that's provided, and you certainly can do it, but it's one that goes on water, and having it go straight is a challenge. So a simplest form, you would take a milk carton or a juice carton here, and tie a couple of rubber bands around it, and have these pencils as like structures where you attach your engine, and your engine is over here. It's a simple cork, which has a couple of slices made through, not totally. So from the top, you would make a slice, maybe with a sharp knife or something, allow a little bit in there, in all four directions. You use two of these slots to feed through them a rubber band. So the rubber band comes like up here, right, and goes down there, and on the bottom it turns around. The other two slots, right, they are down here, so here's a slot really. You attach little fins on both sides. They are shown here. And it doesn't look like an engine, but if you attach these rubbers to your structures here, your pencils, and you twist it, let's say 20 times, and you put that structure now in the water, this will function as a little propeller, right? It will propel your boat, hopefully it's a boat and not a submarine, forward. Again, if there's no stabilizer, most likely this boat, and that I've seen in the past, it will make some weird path, and it's hard to measure it. So you need to do some sort of improvements on it. Yeah, that's one way of doing it. You don't have to do on water, right? You can replace, you can put little wheels here, or the best thing is you can get ideas from the internet. I don't mind having you do something that was done before. But don't use any kits, like I buy this kit for 10 bucks and it's gonna do this. But you have maybe toys around, and you can do something similar of it. I want you to create it, right? Don't use a toy and analyze it. That you didn't fulfill the purpose of it, right? Of the engineering part. So part of this is your own design process, and that's what we want to get across here. So it's not just the physics, right? Don't copy, please. The Turnitin will catch these things, you know. The rubric, I'll show you the lab in the template in a second, but give your name a cool, the toy a cool name, so that we can make a lot of money of it. Make a drawing of it. It can be by hand, like I draw something here, like, you know, like this, and as good as you can on the computer, or you do it on paper and scan it back in. Label all the parts, right? Here's your wheel, and like we did in the past with the moon landing. Tell me how you you constructed the toy, right? What did you do first? What did you do next? How long did you wait? What were the gotchas? Maybe you had to do it twice. What did you learn? You should be able to get these 10 points easily. How is the toy operated? What do you do? Describe what you have to do to make that toy go, and be safe, of course, and give me a good description there. But then you analyze the physics principle. Specifically focus on potential energy, U, and kinetic energy, K, right? What is potential energy? What is kinetic energy? Define those terms. How much energy gets stored? And that you might have to estimate it, right? But say, for example, potential energy is proportional to the number of revolutions, in case this was an N here. You do these propeller designs, or maybe you use gravity. Potential energy equals mgh. I do not know how to do this, but you could convert gravity into motion, right? I don't know. Let's make a car here. Let's make a stand here, and you have some rollers here, and you have a weight here that will go down, right? And there's a string here that will propel your wheel. So if this mass goes down, it will pull the string, and it's probably wound up before, and it will go to the right. So this would be some potential energy there, right? But of course, how you make it, this is just a thought, right? How you use mgh. Some of you might be able to use a spring, and you can use them 1/2 kx squared, where x squared is the amount of compression you applied to the spring, right? This would be your displacement x here. So be creative there. Document it with photos or videos, and then do the physics calculations. So you need to do what's called metrology. You need to measure. Okay, you start here, you stop there. How long? What was the time it took for the toy to reach point A to B? What's its mass? So you need to write the mass, right? You need to know the time is what for whatever distance there was, x equals whatever it was, right? Maybe the toy started fast and slowed down, right? What made it slow down? Maybe it has so much friction, and I don't want you to worry about friction. So don't, you can use it as an argument for it, but don't analyze it, right? The friction part can be pretty messy. And then you're gonna calculate from kinematics your velocity here, maybe your average velocity, right? Maybe you wanna measure your initial velocity, so during the first couple of frames. I don't want you to do a picture video analysis, but maybe you one time measure it, the distance here, one time you measure it there, right? And show me all your calculations and your work. So I think that's it actually for this project. We'll have a bunch of Class Connect session before it's due, which is the March 22, 322, easy to remember. We have about a month now, it's 224 to do that. So come to any of the sessions and I'll help you out. If you're not sure, show me your design and ask questions. Thanks for watching, and good luck with the project. Oh, sorry, there will not be an extra credit part in this project. The next one, the final one, will have one.